I'm Dietmar Küchemann. I'm a researcher in maths education, and what I want to talk about today is some work I did while on the Proof Materials project, which was a research project, a design research project at the Institute of Education, directed by Celia Hoyles. The research followed on from another project at the Institute of Education, the Longitudinal Proof Project, and it also fed into my most recent project at King's College London, the ICANS project, directed by Professor Jeremy Hodgson. On the original Longitudinal Proof Project, we had this item. Essentially what students were told was that we had a strip of white tiles, and around it was a single layer of grey tiles. And the question was, if we had a strip where the white tiles were, there were 60 of them, how many grey tiles would there be? We built in this distractor by showing them 6 white tiles, which happens to have 18 grey tiles, and so there's a rather nice numerical relationship that leaps out at you, but which has nothing to do with the structure of the problem. So we were interested, would students focus on the structure of the problem? You might describe it as, well, for all the white tiles there are some grey ones on top and some grey ones beneath and a few at the end, that kind of thinking, or would they simply home in on the numbers? So here's that an example of a student who did this, where they just worked with the numbers. 6 white tiles matches 18 grey tiles, 6 times 10 matches 18 times 10, 60 matches 180. Here's a nice structural answer. For each white block there is one above and one below, so I times 60 by 2 to find this number. I then added 6 for the 3 blocks on each end. And here's a sort of geometric version of that, a very nice, clear, I think, way of structuring a task. Now these are the frequencies we got for our years 8, 9 and 10 students, and these, by the way, were quite high performing students. They were from the top 1 or 2 sets in the school. Now, 2 things. These are the students getting it right. So the year 8s, the 13-year-olds, about half of them got it right, presumably used the structural argument, probably used the structural argument, coming up with 1, 2, 6. When one looks at the empirical responses where the students give the answer 180, a third of them in year 8 give that, so they home in on the numbers, they leave the structure behind, and it's still about a fifth of them do it in years 9 and 10. That's a substantial minority of high performing students, and this intrigued us, and we thought about the reasons why this might be, and our hunch is that it might well be something to do with the way generalising is taught in maths classes. Often a task is not presented with a sort of generic example like that. It's presented in this kind of way, where you're given a set of patterns presented in a sequence, and students are encouraged to work this way. It seems to become a kind of folk wisdom amongst teachers, amongst researchers as well, and certainly amongst the exam boards, when students used to have coursework where they did these kinds of things as a so-called investigation. The exam boards produced in the UK produced very clear guidelines about how this work would be marked, and the key thing was that students started working systematically, as the exam boards called it. They looked for patterns, they tried to induce a rule, not deduce it from the structure, but just from the numbers. So in fact, often they would just home in on the numbers, forget the pattern. And then those who got top marks were those who could explain the pattern. So that was meant to be something that you do right at the end. Our feeling was that this is the wrong way around. It's encouraging a kind of quasi-scientific way of thinking, which can be useful, of course. If you might have to explore a problem if you can't get into it. It's perfectly legitimate to try examples and look at the numbers that come out and get some hunches. But where the structure is accessible, surely we should go for that first. And the study, therefore, that I undertook was to see whether teachers could teach in a different way. In this study with the Proof Materials project, we used a task a bit like this, or at least the beginnings of this task. Again, presenting a situation generically, presenting one example, but where it's clear what the family of examples would look like, not presenting it in this kind of sequential way where you home in on the numbers. If you try to home in on these numbers, they're quite difficult actually to find a rule that works, because it turns out this is quadratic. So what I want to talk about in particular, and this is what I've written about in the paper, is in one of the schools we worked with on the Proof Materials project, one of our teachers, she had a year 7 class, so they're about 12 years old. They were a set 3 out of 4, so they were deemed to be quite low attaining. And she gave them an activity where she presented them with a scrap of A5 paper with these arrays drawn on, with the children being asked, can you think of a way of counting the matchsticks, and can you show this by colouring the matchsticks? So the colouring is done by the student. And in this one, what one might infer is that she's saying, well, I've got a row of 3, another row of 3, another row of 3, another row of 3. So I can count those quite nicely, either by 3, 6, 9, 12 maybe, or even saying 4 3s back. And then I've got a column of 3, another column, another column, another column. So it's a very nice way of structuring this problem. Now, it's not necessarily the case that this student could go on to say, therefore the 20th would be 21 lots of 20 plus another 21 lots of 20. In fact, what they're asked to do next was to look at a 4 by 4 and a 5 by 5 situation, and again colour it in. Now, the way she did this wasn't quite the same as the way she drew the matchsticks, so one could argue, well, she doesn't really have a sort of strong sense yet of finding a rule and applying it systematically, because she's come up with a different rule here. But it's quite a nice rule. Here she's finding the perimeter, so in this case you've got 4, 4, 4, 4 around the outside, and then she's finding the 3 green columns and the 3 yellow rows. So it's not quite as efficient or perhaps as elegant as her previous method, but it's perfectly nice. And she applies it also to the 5 by 5 in exactly the same way. So she has hit upon a method and is able to use it in some kind of consistent way. And remember, this is a year 7 student in a set of 3 out of 4, so she's not deemed to be very mathematical. For the 10 by 10, she tries to apply the same system, makes a slight mistake. I've tried to enlarge it here, I don't know how well one can see this. Basically, I think she's saying you've got 10 lots of 10 rows and 10 lots of 10 columns. Now actually it's 9 lots of 10 rows and 9 lots of 10 columns, so she doesn't get quite the right answer. So she hasn't quite generalised it, but it's very impressive, I think. And so that's really what the research was about, the paper was about. It was a kind of proof of concept of saying that if we're a little bit more ambitious, and this teacher, it has to be said, she's A, a very good teacher, and B, a very confident teacher. She was prepared to try something out for us. It was not the way she necessarily taught herself, but she was willing to have a go, and that's crucially important. And of course it's difficult for teachers to do that when they're under intense pressures these days, to show that they're performing effectively, that their classes are performing effectively. Pressures from management, pressures from Ofsted. So it's not an easy thing necessarily to get persuade teachers that this is worth risking. But my view, okay, this is just a small example, but my view is that we could go a lot further by being a little bit more adventurous and plunging in a little bit more at the deep end and looking for structure from the start, which is what maths is after all about. Maths is not about just looking for number patterns. Okay, thanks.